all of prob and stats in 20 minutes. Woohoo! Oh. Chapter 1. What is probability? How do you interpret probability? Probability basics, I'll call it. Probability basics. What did that include? Like, well, how do you even interpret what a probability is? A measure of likelihood. 1, it's guaranteed to happen. 0, it's guaranteed to not happen. 0.5, it's 50-50 chance. Will happen about half the time. Probability was 0.1. It happens about 1 out of every 10 times you run the experiment. We're fairly surprised if it happens, right? If you got a baseball player who's a 100 hitter, well, first of all, probably would not be on the team anymore. But secondly, if they were still on the team because their defense was so good, you'd be very shocked when they get a hit, though it does happen sometimes. So it's that kind of idea. Then there's the personal opinion approach to probabilities. There's the repeated experimental approach, and then there is the more theoretical approach, which was what we mostly focused on, based on sample spaces. I'll combine chapters 2 and 1 and 2 here. 1 and 2. Sample spaces, events, which are technically subsets of sample spaces. The classical formula for probability only when the events, the outcomes are equally likely. When you've got finitely many outcomes that are all equally likely, you can write the probability of an event A as being the number of elements in A divided by the number of elements in the sample space. But once again, only when there's finitely many elements for one thing, and they're all equally likely. N means number of. That's the only time you apply this formula. So it means you can't always apply it even with finite probability spaces. We also got permutations and combinations as tools for computing probabilities, especially in situations where outcomes are equally likely, like you're picking, you got 10 people and you're picking 3 people to be president, secretary, and treasurer. How many ways can that happen? And what's the probability that you and your 2 friends are the 3 people picked in any order, say, as a quick mental example of something you should technically be able to solve. I always shared with you, and maybe you felt the same way, that I always feel scared when I have those kinds of problems, like I'm just going to do something wrong, because it's just so easy to misunderstand exactly what to do. I think generally speaking, you did okay on the exam questions, and remember your exam is going to have similar problems. So hopefully that means it'll be okay for you on the final if you put a problem like that. You can come up with really tricky problems in this context, though. You also have the general formulas for those things. They're based on also the multiplication principle. Like initially applied in thinking about, for example, how many license plates are possible in Minnesota, where you have 3 letters and 3 numbers. Well, if the letters have to come before the numbers, and if you allow repeats, it's 26 times 26 times 26 times 10 times 10 times 10. Okay, and if you allow it to go the other way, then you got to multiply by 2 as well. Into chapter 2, we have the axioms of probability. Which included, for example, the fact that the probability of the sample space occurring is 1. In other words, something has to happen. Guaranteed. You also had the fact that probabilities of any event are always non-negative. And then the most important one, you might say, is the addition rule for mutually exclusive events, which I'll just write in the case of 2 events, just to keep things simple here. If A and B are mutually exclusive, meaning their intersection is the empty set, then the probability of A or B is the sum of their probabilities. This is if A intersect B is the empty set. This can be extended to finitely many mutually exclusive events that are pairwise mutually exclusive. And even infinitely many, that as long as it's countably infinite. You can use these things as axioms, meaning you assume they're true, to prove other things. Theorems included the fact that the probability of the empty set is 0. The probabilities are always less than or equal to 1. The complement rule, the probability of the complement of A is 1 minus the probability of A. Those kinds of things can be proved. I don't remember if I put a proof on exam 1 or not. Maybe I did, maybe I didn't. I don't remember. If I did, then it's fair game for your exam. Maybe modified, maybe a slightly different proof. I can't guarantee. I don't remember what the problem was, if there was one. Then we got into more complicated kinds of rules. There's the general addition rule. In general, the probability of A union B, A or B, is the probability of A plus the probability of B minus the probability of A intersect B. In all these things, by the way, we also had our problem-solving tools like tree diagrams. Boom, 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 that kind of thing. Problem-solving tool. Technically, sometimes charts are helpful. Another problem-solving tool, help you think through things. Venn diagrams are helpful, right? And sometimes instead of using the abstract formulas to solve a problem, it's just much easier to use a Venn diagram. So if that's all you're after is the answer, go ahead and use a Venn diagram. You don't have to write down the formula unless it seems easier for some reason. We also had conditional probability. Probability of A given B, by definition, is the probability of A and B divided by the probability of B. That leads to the multiplication rule for any two events. The probability of A and B is the product of the probability of B times the conditional probability of A given B. By symmetry and the arbitrariness of our symbols, that also must equal the probability of A times the conditional probability of B given A. Even though this formula would not give that to you directly. There would be a similar formula that would give it to you. But it's got to be true by symmetry in our symbols. That's the general multiplication rule. Independent events are those that by definition satisfy the conditional probabilities equaling the ordinary probabilities in both cases. And therefore, we also have the multiplication rule for independent events. Probability of A and B is the probability of A times the probability of B. I labeled these two things a definition and this thing a theorem. I thought that made more sense, and Dr. Wetzel, when he teaches the course, agrees with me. The book does the opposite labeling this a definition and this a theorem. In a sense, it's like a little easier to prove. I think that's their reason they did it that way. But both of these conditions, either this one or this one, are equivalent for A and B being independent. This formula, the multiplication rule for independent events, I called the most important, perhaps, equation in applied math right there. We use that equation all the time in this class. Maybe you were not aware of that, but we did. In, for example, deriving formulas for the PMFs of geometric and binomial random variables, for example, which brings us into chapters 3 and 4. 3 and 4 about random variables, discrete with chapter 3, continuous with chapter 4. You've got your general formula. Maybe I'll add chapter 5 in here. You got your general formulas. We're already at 10 minutes here. So what does that include? That includes well, your general conditions, the fact that, for example, with PMFs, you want the sum of all the PMF values to be equal to 1, for example, and all the PMF values are greater than or equal to 1. That applies to PDFs for continuous random variables as well, for them to be greater than or equal to 0. With PDFs, you also want them to integrate to 1. You got general formulas for expected value. For example, in the discrete case, the expected value of x is this kind of thing. Overall x. In the continuous case, it's an integral instead. There is keeping the distinction in the discrete case that the PMF actually gives you a probability, the probability that capital X, the random variable, equals little x. Whereas in the continuous case, a PDF, the values do not give you probabilities. You have to integrate them to get probabilities. That's the way it works. That's why I like using different terminology for them, even though the book doesn't. So you got those kind of abstract formulas. You've also got abstract formulas. Well, that is for the mean here. There's also the second moment. Second moment, expected value of x squared. And the variance, by definition, is an expected value as well of x minus mu squared, but that's the computational formula is what we always use, that the second moment minus the square of the first moment. You got also moment generating functions, and the fact that they're used to compute moments by differentiation and plugging in 0. The first derivative evaluated at 0 is the first moment. The second derivative evaluated at 0 is the second moment. If you're after the variance, don't forget to do this, though. Second moment is not the variance, even though it feels like you wish you were done when you find that second moment. And then you've got the particular formulas for all of our special parametric distributions. In the discrete case, we had geometric, binomial. I also talked about uniform discrete distribution. What else did we have? We also had hypergeometric and negative binomial. This is the first time I taught those, but they did show up. You should review them. And Poisson. Those are all discrete. For continuous, we had gamma and its subdistributions, exponential and chi-square. We also had uniform, right? Graph is horizontal line over some interval, and normal. Those are the main ones for continuous. I got there was exponential we use, and normal we use the most. We also talked about actuarial science, the lifetime random variables. We also did a lot of extra things besides the actuarial science that included things like the CDF method. What is the CDF method? The goal of the CDF method is to find the PDF, actually, in a special way. You first find the CDF, capital F of x, by doing this. And then in the continuous case, at least, you differentiate this to find the PDF. In the continuous case, can you use this in the discrete case as well? Yes, you can, but you don't differentiate. You compute a difference in the discrete case. We never really did an example like that, though. We only did continuous cases. We use this a fair amount for a couple different examples. I think we used it, for example, to verify that if z was standard normal, then z squared was chi square with 1 degree of freedom. You remember doing that? We used it for some other situations as well. I think we used it to like for on the test, I told you what to do. It was our difficult problem, long problem description, like to compute the distribution of the maximum of 2 uniform or the exponential, I forgot, on the test. Maybe I'd modify that to be the minimum. If I do, I'll probably give you a hint about how to think about it, but it's worth you thinking about. Like if X and Y are uniform or maybe exponential independent random variables, and you take the minimum of them, what's the distribution of the minimum? I think we did the maximum on the test, I think. I encourage you to think about that. I'd probably give you some hints again, and maybe even over email over the weekend here. Running low on time. We also did the multivariable distributions. In particular, focused mostly on bivariate with 2 random variables. You got the joint distributions, PMFs in the discrete case, PDFs in the continuous case, adding up values in the discrete case, integrating in the continuous case. You got the expectations, including, for example, the expected value of X times Y. And you have things like the covariance, which the shortcut formula turns out to give you the expected value of X times Y minus the product of the expected value of X and the expected value of Y. You got the definition of independence. Essentially, the joint distribution is the product of the marginal distributions. I forgot to mention the marginal distribution 30 seconds ago. You got the joint distributions and the marginal distributions. Let me put that word up there. Marginal, because with the discrete case, they really are in the margins of the table. In the continuous case, you have to do a single integral to find them. That's the definition of independence. You also have the fact that if 2 random variables are independent, then the covariance is 0. But that's not an if and only if. If the covariance is 0, that doesn't necessarily mean X and Y are independent. We wish it did, but it doesn't. We did some tricky problems involving conditional distributions as well, sometimes integrating over triangular domains. And the curve of regression. I mean, in class, it was fairly tricky. On the exam, the problem was, I gave you help. It was about as easy as it could be for such a problem. Understanding what the curve of regression gives you. There were 2 curves of regression. Technically, there's also correlation in here. Then we got into stats. Chapter 6 was descriptive statistics, but did include some real fundamental things besides just a bunch of graphs. Like what's a population, what's a parameter, what's a sample, what's a statistic, what's a random sample, what is a statistic based on a random sample? And we really approached things abstractly. A random sample was n independent and identically distributed random variables. And a statistic like X bar was a formula based on those. And that was unbiased. Expected value of X bar is mu. The mean of the mean is the mean. S squared, sample variance, was also unbiased. Sample standard deviation was not. Chapter 7, it was more theoretical. About out of time here. Real quick, just think with me here. It was more theoretical. More about unbiased estimators. The variance of X bar. Method of moments. Method of maximum likelihood estimators. Moment generating function fingerprint theorem, and what came up on the last exam, how to find the MGF of X plus Y when X and Y are independent. Central limit theorem. The beginnings of confidence intervals goes into chapter 8, more on confidence intervals for the mean, and also hypothesis testing, probably the hardest subject, hypothesis testing for the mean, and also the variance in there. Well, the variance was in chapter 10, which we only briefly talked about and you won't be tested on. We got into the proportions in chapter 9. And then regression here. You will not be tested on sections 9.3, 9.4, or anything in chapter 10, even though I did talk about those things. Okay. And they would be good for you to learn more in depth for applied stats. I'll tell Dr. Wetzel it would be good if he does go over those in more depth. All right. Have a good day.